So just by a show of hands here, how many people have heard of Jensen's inequality? 2 of you. Right. How many people have heard of the flaw of averages? Anyone read the book? One of you.
Well, that's why we all like you.
Okay, so I want to, the flaw of averages is a set of systematic errors that occur when single numbers are substituted for uncertainties. And let's just jump in here with a quick example. It really does explain why everything is behind schedule, beyond budget, and below projection. So imagine you're in the software business and you're sending out a new package. It consists of 10 subroutines. The calling routine is already written, so all you need are the 10 subroutines, and you're out the door with this thing. Anyone involved in the software industry at all? Are you ever uncertain about how long it will take to finish a software project? Has that ever happened to anyone? Okay, all right. Oh, and by the way, following up on what Michelle said, so suppose that from history, these things average 6 weeks. Each of these subroutines done by 10 separate teams will take 6 weeks on average. Of course, what happens is you go to the team doing subroutine 1, you say, how long will your subroutine take? They say, gosh, we're not sure. And then you say, give me a number. What are we paying you for? And by the way, give me a number is the fork in the road to hell. You do not recover once you have limited the uncertainty to a number. One of the things I'm here to teach today is that you don't have to do that anymore. There's a way to communicate uncertainty in an unambiguous, actionable way. But at any rate, you go to all 10 team leaders and they all say, I don't know. And you say, give me a number, damn it. And they all say, well, you know what? On average, it'll be about six weeks, right? Now you go to your boss. Boss says, when do we launch? And you say, well, I'm not sure. The team leaders aren't so sure about when they'll be done. And the boss says, give me a number. I said, well, listen, I can give you the average. We just settle for the average, boss, right? And the boss says, sure, if that's all you can give me. Well, each of these is going to take 6 weeks on average. So, on average, we ought to be done in 6 weeks. Now, let's just see by a show of hands, what is the chance we're going to be done in 6 weeks? 100%? Anybody? 50%? 1 in 4? 1 in 10? Got some 1 in 10s, all right. 1 in 100. Got quite a few 1s in 100. Okay, 1 in 1,000? We have some 1s in 1,000. Okay, first comment. Is this a really uncommon, kind of straw man example? Or do you really have schedules? And do you really have uncertainty? Right. This is everywhere. Second comment. There is only one right answer, by the way. But I noticed a broad distribution of opinion in the room. Now, okay, the right answer, by the way, is 1 in 1,000. Who said 1 in 1,000? Could you explain that to a 10-year-old? Let us suppose that we're going to assume the following. This is true. The average of each of these is 6 weeks. Why is the chance only 1 in 1,000 of being done in 6 weeks? Let's say each one has a 50% chance of being greater or less than 6 weeks. Then what?
Then I think you have to go, is it about 50% times 50%? It's like factorial. I was trying to remember back to high school.
So I like your intuition, but you failed with a 10-year-old. There is only one way to explain this to a 10-year-old or your boss, who's ever smarter. Someone else want to take a crack at it? Yes?
There's only one combination where everything delivers on time.
Not just one combination. No, you're not getting to the 10-year-old. Please. What?
It's the odds that a single one of your projects goes over 6 weeks. A single one of all the team goes.
Well, that is true, but how do you express that in a way that a 10-year-old is going to grasp?
That's not going to happen.
What?
It's not going to happen.
No, but that didn't prove to me that it's not going to happen. I want the 10-year-old to be able to derive that it's not going to happen. Okay, we're taking too much time on this. Imagine each one has a 50-50 chance of being over or under. Well, being under is like flipping a head on a coin. Oh, so all we have to do is flip 10 heads in a row. Got that? Okay. So, get this. We use averages. You'll say, oh, we'll be done in 6 weeks. In reality, there's one chance in 1,000 of being done in 6 weeks. Can you grasp that this is not close enough? Even for government work. I don't know if there are any government workers here. No. Done in 6 weeks, one chance in 1,000 being done in 6 weeks. No. You cannot run your organization that way, and yet you probably do. That's why I wrote a book about it. All right. Just one little comment here. In the book, I've come up with what I call red words and green words. So part of the problem, how many people in here have had at least one statistics course in their career? Okay. And for how many of you was that like the high point of your week? One or two of you. Okay. What I tell people is, I don't assume any statistical background. If you've had extensive coursework in the area, then it usually doesn't take more than 45 minutes to repair the damage. We'll find out soon. Anyway, so there are all these words that statisticians use. I call them red words. And John Wiley, bless their hearts, the publisher, printed them in Dracula font. Okay? The formal definition of red word is something that cannot be uttered in a singles bar. Or these days on your, like dating profile, right? So let me give you an example. Let's see how many people know what this is. Here's the green word. The green word is uncertain number. You got that? How long will task 1 take? How long will these are all uncertain. How long will the whole damn project take? What's the red word for that? You've all had a statistics course? Show of hands? Huh?
Variance?
No. By the way, this is why I don't use red words. It's random variable in Dracula font. All right. So let's go back to the model. Here's the schedule model. First of all, let me convince you. Well, one of the things I can do, by the way, is I'm going to model uncertainty here. Like, that could happen, or that could happen, or that could happen. One of the magic things that we've done at probability management is figure out how to store thousands of scenarios in plain Excel. No macros, no add-ins. And we'll get to that, because now it turns out that Power Pivot and Power BI just play right into our game here. It's just an amazing breakthrough, things we've been doing with Power Pivot. But anyway, so a big problem here is explaining this stuff to people. And trust me, we have 1,000 scenarios stored in here. We'll get to that in a minute. But let me give you a more sobering example of the flaw of averages. So consider a drunk wandering back and forth on a busy highway. The state of the drunk is average position is alive, but on average, he's dead. Not close enough, even for government work. Now, again, this has been around since, well, this Jensen's inequality thing I told you is exactly about this subject, right? What a stupid name. For one thing, the guy's name was Jensen. He was Danish. So why did they call it Jensen's inequality? But even then, it doesn't have a lot of cachet. So I call it the flaw of averages. And because, I noticed that people were sort of confused about this. And by the way, this is a fairly self-selected crowd to be like analytical at a conference like this. Yeah, imagine what happens when you go off to your neighborhood grocery store. Well, anyway, So this is really like a public relations effort. And so the Flaw of Averages has an audio logo. Everyone know what an audio logo is? Right. What's that? No. Intel. Right, okay. So here's the Flaw of Averages audio logo. Now let's go back to the project for a sec. Let's put this in the context of like a business that delivers software. And the customer said, you got to deliver it. You know, can you give us a deadline when you'll be done? And you were smart enough not to say 6 weeks. You gave yourself some wiggle room. You said, oh, we can do it in 7 weeks. Easy. And so you accepted a $100,000 per week late penalty for being late. Now, here's where probability management comes in. First of all, what does that mean? Have you heard of data management? That is for storing and retrieving numbers, as in, give me a number so I can perpetuate the flaw of averages. Probability management is about storing and retrieving distributions, that is, ranges, scenarios of outcomes. And we've developed this wonderful open standard to do this. And let me show you how I'm going to do it in this example. I invented a data type called the SIP, like think bit and SIP. The SIP stands for Stochastic Information Packet. It's a column, in this case, of 1,000 possible outcomes for each of these tasks, durations. How many people have used Monte Carlo simulation? Monte Carlo simulation could have been used to generate these. The simplest way to think about probability management is it's Monte Carlo simulation running off of auditable data as opposed to numbers being generated randomly, right? So the numbers get generated earlier. We'll get to that in a sec. But anyway, those numbers can all be run through the model. And so, for example, when I was doing this, right, I'm explaining this to you. Well, that could happen, or that could happen, or that could happen. And let me point something out. You'll notice I haven't gotten to 6 weeks yet, right? That one was 7.1 weeks, because this is the one here. It's the maximum one. You're not done till the longest one is done, right? I have found in talking to people that I do not need to scroll through all 1,000 scenarios. I tell them there are 1,000, and then they get it right away. It's not like I've ever gone to someone who said, like, I got to scenario 999. They said, I still don't get it. I go to scenario 1,000. Oh, now I get it. No, people get this right away because it's animated. It's interactive. Okay, so let's scroll down to the average again. And, so let's look at some things that could happen here. So the outcome based on the average inputs is will be done in 6 weeks with 0 penalty, right? But of course, as I scroll, 7.7 weeks, 68,000, 7.8, 82. And you know, if you're running a business, you might want to know what the average values of these are. So you get the difference. There's the value given the average assumptions, and then there's the average value. The drunk is on the center line, or the drunk is dead. You want to know the truth. So let's pop down here, and you'll see it is incredibly easy in Excel to run all 1,000 scenarios through here and discover that on average, it will take you 7.8 weeks with a penalty of over $86,000. Now, here's where it gets exciting. This is a native Excel sheet, no macros, no add-ins and things. So suppose you now go back to the customer and you say, oh my gosh, we're really worried about this. Would you be willing to reduce your penalty to 50,000? And they say, sure. But then you're going to have to accept a 6-week deadline. Oh, watch this. Every keystroke ran all 1,000 scenarios through this model. Let me undo this. This is real-time interactive simulation, right? Okay, so watch down here. Undo, undo, right? 7 weeks, $100,000. Redo, redo. Ooh, 92,000? I don't like that. So I go back and I say, well, gosh, would you let us have an 8-week deadline? And they say, sure, if you accept 150,000. Sold. We'll take it. That was interactive simulation. What is the big deal with interactivity? So we do have varied backgrounds in here. I want to start with something that everybody understands. And but how many people have read Thinking Fast and Slow by Daniel Kahneman? Sort of talks about System 1, the very fast mind, and System 2. Anyway, here's something everyone understands. The differential equations of motion of a bicycle. The thing is, you do not learn these through the seat of the intellect, but through the seat of the pants. Kahneman had a much better name. He called them System 1 and System 2, but you know, I was talking about this stuff years ago. I call it the seat of the intellect and the seat of the pants. And you need to connect those two things together. And you know, you can't do that unless you're in an interactive environment. So let me just do another example of the flaw of averages here. Get rid of that one. Okay, so you just saw why everything is behind schedule. Well, that's it. That's the reason. That's it. It's a little more complicated than that, but not much. So let's look at why everything is below projection. Well, we're ordering electronics for the Christmas season. We have to order it 6 months in advance from China. The cost per unit is $30. The selling price is $40. The demand, that's uncertain, right? Anyone ever been faced with anyone involved in supply chain or anything and uncertain demand? Don't they say that demand is sometimes uncertain? Yes, they do. All right. You order 100,000, of course, because that's what you expect. Oh, that 100,000 is the average. Everyone agrees. It's uncertain, but we put the best minds on it, and we expect it to be 100,000. And you know, like a fairy walks down a moonbeam and talks to the CEO and says, psst, average demand is 100,000. And the CEO says, well, can you give me like the full distribution? The fairy says, I'm not God, I'm just the mean fairy. Here's the mean, take it or leave it, okay? So let's assume it is the correct mean. We order 100,000. Now, the boss says, what's the profit going to be? Well, let's look at this. We ordered 100,000 at 30, so that's like $3 million. Oh, but we sold 100,000 at 40, that's 4. So hey, looks like profit's $1 million. Of course, you're not certain, are you? Because you're not certain about. So the boss says, what's profit going to be? You say, I don't know, boss. I don't know what demand's going to be. Give me a number. What are we paying you for? And by the way, if you really try to force a distribution on the boss, they'll say, well, you're fired. I'm going to hire someone who can give me a number. And this way, what you find is that a lot of people in high positions are just very lucky because they're the ones who didn't know but happened to give the right number. So at any rate, what do you think the average profit is here, folks? Average profit. The profit of the average is $1 million. Average profit? $1 million?
Less.
Less, you say. Why do you say less? Well, think through it. Can anyone prove that it's less?
Can't be more.
Now you're getting somewhere. Tell me this again.
It can't be more because we're only going to order 100,000.
You're only going to order 100,000. Okay, you nailed it. But now make your argument here. So if demand goes down, what happens? The profit goes down. And if demand goes up, Wyatt? Nada. Very good. So let's see what happens. This, by the way, appears in this little sales statement here. Sales, well, if actual is greater than the ordered, then you sell the ordered, otherwise you only sell the actual, right? Because the ordered is all you can sell. Good. And what does that result in? So that results in a profit of the average demand of $1 million and an average profit of 600,000. Close enough? No. Another one of these really esoteric straw man problems. Oh, you'd never see anything like this in real life. Okay, here's another little question for you. This is what the distribution, by the way, the distribution of profit looks like. You're maxed out at $1 million. Of course, there's nothing over $1 million, as Wyatt correctly pointed out. You know, where were you when your company needed you? Okay, so little question for you. Obviously, we did not have enough in stock to take advantage of the upside if demand was higher. So obviously, we should be ordering more, right? Or should we be ordering less? How about this? Think companies ever have to make decisions like this? Occasionally. Let's just have a show of hands. How many people think we should order more? How many people think we should order less? How many people don't know? Trust me, that is the only right answer. You don't know. You can't do this in your head. Don't even try. All right? I'll tell you, this was actually a problem that I developed for one of my textbooks. And I designed the problem to prove that you should order either more or less. I'm not going to tell you which. And then I ran the simulation, and I got the answer I was not expecting. And so instead of trying to figure out what my thinking was wrong, I said, well, what's wrong with my simulation? What's wrong with my damn simulation? Where did I? No, it was what was wrong with my brain here, okay? Well, watch this, folks. So easy to find out. So easy to find out. Let's put in 120,000. Now our average is 279, right? Let's put in 80,000. And by the way, I could run the Excel solver on this thing too, and actually find the right amount. Okay, at 80,000 we're up to almost 680, all right? Do I need to convince anyone at this point that there's a problem here? There is an issue in dealing with uncertainty. And let me show you where the SIP came from here. So, and then I'll show you how this stuff basically works. Where's my forecast? Here it is. All right. The problem begins with forecasting. So, how many people are involved in forecasting? And what comes out of the forecast? A number. Well, not really. It turns out that all forecasting methods known to man allow you to extract a distribution. So I've just used a word, it's the only blue word in the book, probability distribution. How many people think they know what a probability distribution is? it's not that easy a concept. And yet, it's equivalent to a SIP. So suddenly we have a way of communicating probability distributions. Heck, it's just a SIP. It's just a column of numbers in Power Pivot or Power BI or Excel. It's unambiguous. It's auditable. Anyway, so let me explain this whole process. You do it differently for different kinds of forecasts. In this case, I have got a 95% upper and lower bound. And so here's how you deal with distributions. Because you get it out of the forecast. Right. And what happens next? So don't even waste your time forecasting unless you're going to forecast a distribution, which could get plugged into a model, which could give you the correct answers. So let's do this in Excel. This is just a very primitive forecast, but trust me, I can get a distribution out of any forecast. So here we had like years, and we had sales, and we assumed some linear relationship. We ran a linear regression. It's the lin-est formula. And one of the things that comes out of the lin-est formula is the degree of error in your forecast, right? It's called the standard error. And by the way, you don't need to know how to do this, right? As long as someone in your organization does, because it's now data. So this is a huge change in sort of in business process. At any rate, look what happens if I had plugged in a different data set. Plug in this data set here. Oh, I got a much narrower distribution. Right, but that wasn't the data set I had. I had this data set. And so 1,000 trials later, and I'll show you now how this thing works. This is what we call SIP math. It runs off the Excel data table. In native Excel, nothing else needed. It runs in Power BI and Power Pivot. It's just like you can just make a natural statement in one of those environments, and boom, you get this. All right? So it just means it's another dimension. You store these trials. So anyway, there's that SIP of demand, and I copy it, oops, and I paste it over to here, to my demand library. Boom, done. Get how that works? So we have this open standard for modeling this stuff. The standard is available. Actually, let me pop into another presentation here. Run down here. Okay, oops. Hey, come on. How do I start this thing up in the slideshow where I want it to? I want to start down there. Is there a way to, huh? What is that? Shift F5. Oh, I would have figured that out sooner or later. Hold on. Great, thanks. So what are we storing? Arrays of data. That's not very exciting, is it? I mean, we can do that today. But we're storing them with metadata. We're storing them in Excel format, XML, CSV, JSON. And there are all these tools that can then tie into this stuff. So in particular, Excel, well, like 500 million installed users, that's a nice way to come out of the box with something like this. And now Power Pivot and Power BI, I mean, it's even more amazing the things we're able to do. But many, many other products, I mean, just tie right into this right away. So let me sort of show you how it works. And I think the best thing to do, how many people, by the way, are familiar with the data table in Excel? It's kind of a messy thing, you know. You can't. I call it like a folk art, you know, like learning how to play the banjo. You can't read the banjo instruction manual and start playing the banjo. You have to find some old banjo player to show you how to play the banjo. Of course, now we have YouTubes for that. So I do not encourage you to learn how to use the data table. We've built some tools, some free tools at Probability Management that will help you do this. But you have to be aware, at least, of what the incredible power is. So,
and we have YouTube clips that'll show you how to do it on our website.
yeah, and a bunch of free tools and things. So let's start this with dice. So, everybody basically knows. Everybody basically knows how dice work. The way we communicate the uncertainty of dice is as SIPs. These are, each SIP has 10,000 die rolls in it. Right? 10,000. This is an index statement that points into the SIP. So roll 1 was a 4, a 6, and a 5. Roll 2 was a 3, a 2, and a 6. I haven't memorized all 10,000, but they are auditable. And I do remember that trial 9,765 is 3 ones. I'm putting my money on it. Boom, look at that. Okay, now let's start doing SIP math. So I say equals that cell in native Excel. I hit the enter key, rolls 10,000 trials, and it looks like that. It's equally likely 1 through 6. Of course, you knew that, right? How many people know what happens when I add the rolls of 2 dice? What will that shape look like? How about that? Triangle, actually, normal is close enough to win full points. It's not bell-shaped. It is, in fact, triangle. Kaboom, that was 10,000 trials. Right? Now, that was a simulation, right? That was 10,000 trials, right? And what I have to point out here is, so how many people have done simulation? Oh, only a few of you. But like when you do a simulation, you can't like undo it, right? That wouldn't make sense. I mean, it's like virginity. No, you can undo it. Control Z, minus 10,000 trials. Whoa, it's just data. Okay, now let's see how good you are at this. What if I multiply those 2 dice? What is that going to look like? Huh? I don't even know what to call it. It's just a big god-awful mess. But that's what happens. So if you are in a business situation, like you show up at the crap table and they say, oh, sorry, we got a new game today. We're multiplying the dice, not adding them. Well, bingo, you say, hey, I'm putting my money on 6 and 12. But life is a crapshoot. So what's going on here is, for those who know what the data table is, on this back sheet, there is a data table. And we have tools for creating these things, so you don't have to know how to do it. And again, there's an equivalent way to do this in Power Pivot or Power BI that doesn't require the data table at all. So quickly out on our site, here's the page on SIP Math with videos. Here are a bunch of models. There is a model that I've got a single model that shows why everything is behind schedule, beyond budget, and below projection, which is going to be on the conference website. So I uploaded that. I just want to make sure you have some good resources here. So I'll show that at the end if I have time. But it's just one model. Go out to the conference website and just download the one example that does all these things. But now let me show you some additional stuff here. So this morning in the keynote, they talked about how Business intelligence is a rear view mirror, right? Oh yeah, but now Power BI brings us up to the present. Yeah, but probability management goes into the future. We give you what's going to happen in the future. Do we know for sure? Of course not. That's why we give you 1,000 futures. But that's way better than a single future. How many people have heard it said that simulation is only as accurate as the model of uncertainty you put into it? Anyone heard that said? That's baloney. Let me give you an example of a very useful simulation. What's the last thing you do before you climb on a ladder to paint the side of your house? You shake the damn ladder. I know you do. Okay, some people deny this when I'm done with this lecture, but you shake it. Right. Here's the bad news. The distribution of forces when you shake a ladder is quite different than when you climb on it. Right, so you're going to stop shaking ladders now that you know you've been using the wrong distribution for all these years? No, you're going to keep shaking ladders. So let me demonstrate, I want to make sure that there's so many wild things going on in this space. Let me first show the tools that are available. So at probabilitymanagement.org, we are a 501c3 promulgating this whole approach of probabilistic thinking. Michelle pointed out, we've got sponsorship from some big companies. And they've developed communities of practice in this stuff. Look at how easy it is to apply this stuff. Now, this is a free tool available at our website that helps you build these data table models. And I'm going to build one first that just has random numbers in it. So I'll go equals, rand, open paren, close paren. Now, this is kind of abstract. That's a number that goes between 0 and 1. But for those who want to see the power of this, okay, so I'll square it. And the tools here, now I'm going to create a model with 1,000 trials. The tools are free, and the model doesn't use the tools. The tools are a goose that lays golden eggs. And the goose is free. This is ridiculous that people don't know about this yet. Well, I mean, some do, and now you do. Anyway, I just clicked OK, and bingo, it created a new sheet where that data table is going to happen here. So there's the PM table sheet, right? Then I click Define Outputs, and let's call this Test. I click OK, and 1,000 trials later, there is a range called test. And I can find statistical properties of that, like the average, right? Well, let's try the average. So I can say equals average of test. Okay, very good. And I press the F9 key. Oh, I can also make a nice big histogram of that. I'll click over here and put something there. So I know I'm getting kind of abstract here, but I want you to see the raw horsepower of this. So every time I press the F9 key, I get a different 1,000 trials now, right? It's still squirming around a little bit. Let's put this up to 100,000 trials. I mean 10,000 trials. Here, 10,000. Okay, so that's 10,000, 10,000, 10,000, 10,000. That's still a little squirrely. Now we will go up to 100,000. Okay. 100,000, 100,000, 100,000, 100,000. Oh, well, let's go to 1,000,000. Uh-oh. 1,000, 2,000, 3,000. 3 seconds. I'm a busy guy. I can't wait around all afternoon for my simulation results. What the hell is this? All right. So I typically limit myself to 10,000 or 100,000. Now, learn more about the tools. They're on our website with instructional videos. Let me show you now how the world is all kind of evolving here. Is this anything really new? The answer is, in a certain sense, no. So was the smartphone new? No, there were cell phones and computers and touch screens. What, like you stick three things together and that's new? No. No, what was new was a communication protocol that turned a smartphone into a node in a network of 100 million other smartphones. That was new. So we've done nothing new here. Columns of numbers? No. The Greeks probably knew about those. They're called vectors. Right. Monte Carlo simulation, 1947. Databases, been around for a long time. But by creating a common communication protocol, whoa, suddenly we're a node in a network of all kinds of crazy stuff. And let me show you some of that. I mean, this stuff, some of this stuff I've only discovered in the last few weeks. The fact is, I really have only discovered Power Pivot since January. Anyone know who Howie Dickerman is? He works in he helped develop the DAX language. And, he came to our annual conference down in San Diego. And working with Howie has been very exciting because suddenly we realized that if this simulation in Excel is like, you know, an atomic bomb, then Power Pivot is a hydrogen bomb. I mean, it's just like orders of magnitude more powerful. So I just went in here and I copied the SIP, the demand SIP from my below projection model. And I go out here to the web and here's something called guesstimate. That you build probabilistic models on the fly. And I've built the same model just out here on a website, right? And I've got it all hooked together. It tells me the profit's going to be $1 million. And I just pop out here on the website, and I jump up here to the demand cell, and I paste in my SIP, and it says, oh yeah, your average profit is 600K. And actually, it's just sort of approximating. If I go to scientific notation, if we look in here, it's actually 601,147. Well, it's exactly the same number I got in Excel. It's auditable. That's been one of the big problems with simulation. The accountants go nuts. Oh, it gives you a different answer every time. So no, this isn't a simulation. This is a deterministic model. This model has 50 million numbers in it, by the way. We hear you guys are good at auditing stuff. Why don't you go audit these 50 million numbers and come back and see us after lunch, okay? Let us get some work done. Okay, let me show you another thing. Wild thing. So here is a website called random.org. They generate random numbers out of atmospheric noise, for God's sakes. And that's kind of interesting. How many people know who John von Neumann was? No. Most famous mathematician of the 20th century, invented the computer, by the way. But one of his famous sayings was, anyone who thinks that they can generate random numbers from deterministic algorithms is living in a state of sin. And the fact is, that's probably true, but not from this random air molecules bouncing around. And this outfit, believe it or not, actually sells these random numbers to like lotteries and things like that, right? Let's get 100 numbers. And so now I say generate the fractions and then export, as SIP XML. So I'll export this thing in the format that SIPmath reads, right? It's part of the network. Crazy. I just sucked 100 numbers out of random noise. How many people have heard of the second law of thermodynamics? So I asked this guy, he's a professor at the University of Dublin. So if you get money for selling random noise generated by atmospheric nonsense, and you buy gasoline and put that in your car and drive down the street, have you violated the second law of thermodynamics? I don't know. He's coming pretty damn close. So let me show you some real stuff. We've got about another 3 minutes, maybe. Is that right? Okay. So talk about eating your own dog food. Let me draw up. Oh, and then I have to show you Power Pivot too. So here it is. All right. So we are working. I use this in my consulting. I'm a consulting professor at Stanford University, which is a nice way of saying I have to support myself through my consulting. My time to probabilitymanagement.org is volunteered. But we're working with a large power utility in the Bay Area, helping them roll up the risk across a big gas pipeline. Now, one of the things you could not do in the old days with simulation is add simulations together. They weren't additive. Why not? I don't have time to tell you, but they weren't. But this is additive. In other words, I added the numbers in one sip of dice, the numbers in another sip of dice, added them together, boom, I got the sip of the sum of the dice, right? Because it was just a simulation on the spot. So here I have this thing. Now this is just a totally sanitized model, and I've got just a regular Excel filter in this thing. And, oh, we're looking over assets. We've got valves, we've got pipes, we got, fittings and everything. And here's like safety risk, financial risk, reliability risk. It's like rolling up a bunch of dice. And I can just pop up here the assets and I say, oh, let's just look at the risk across the valves. Click. And by the way, that was 10,000 trials, right? Oh, well, let's just look at the risk in the valves that are in the north. Every keystroke is a 10,000 trial Monte Carlo simulation. How about that? And now let's start getting to the real deal. And again, this is all sort of like it is completely disguised, sanitized data. But I mean, as we're learning this new technology, and really we've just been learning this stuff in the last few weeks, and it just got, I mean, the further we get into Power Pivot, the better it gets. So here it is. Okay. How many people have worked with Power Pivot? Let's go over to Power Pivot. And okay, so there's 1,000,000 rows of data. 1,000,000 rows of data representing 100,000 pipeline segments, 100,000 segments. Bunch of rare events going on. Gosh, how do I roll up the risk across those 100,000 segments? With, by the way, I have to have 10,000 trials worth of data too. I mean, 10,000 trials because it's a rare event and everything. And well, okay, let's see. What happens if I drag impact down there and then I drag trials down there? Okay, that did it. That was that. Sorry. Just rolled up the risk across 10,000 hypothetical pipeline segments. That SIP can now be used in Excel. Can be shipped off to anyone else. Oh, but wait, maybe I wanted to know what the risk was by region. Okay, now I have 4 SIPs. Anyway, there you have it. What can I tell you? I mean, they laughed when people said that you could cure bacterial infections with moldy bread. Today we call it penicillin. It's a miracle. Excel and Power Pivot together, are doing for simulation what cold fusion would have done for energy if it had actually worked. So I hope you'll visit our website. I'm doing a lecture series in a few cities. You can just check it out here. The free tools are outrageous. Oh, questions? Yeah. So There might be some questions after this. And we're good for like until 11. Yeah. Or are you speechless? They're speechless. Well, wait, does that mean I can keep going? Oh, okay. Okay, well, let's see. Maybe I should give you some choices. First of all, I better get this out of here because it's like 30-some megs. Okay, one of my favorites. Oh, yes, here's a favorite. Here's a favorite. So, yeah. Oh, yeah. Okay, so we actually don't have until 11. Very good. Okay, tough. See you guys around.